Let's talk about the problems of the LU decomposition if we do it in the way we did in the last video. First, let's recap what's going on. If this problem is given, then the first step is let's decompose the coefficient matrix. And how do we do that? We take the first line and eliminate this entry. So this entry has to get 0. And how do we do that? We take the second line and we subtract a third of the first line, and then we get 0 here, the desired 0, and here we get 4 divided by 3. And where does that number come from? That number comes from the division of this entry divided by that entry. And so if we have the following problem, then our algorithm, now we divide this entry by that entry as we did here, and in this case we get a division by 0. And so our simple algorithm we programmed in the last video will crash. So being a student, I would say, okay, we have to implement the if statement. If this entry is 0, then we have to do something else, and the problem is solved. But a 0 will bring a crash, and now a close to 0 will also bring problems, and these problems are even worse. So let's talk about a matrix of that. Let's say we have a matrix of size 100 by 100. And let's have some random numbers being the coefficients in this matrix A. We will use uniformly distributed random numbers in the interval 0 to 1. And now let's modify that matrix in the following way. And here in this block we will use random numbers which are not 0 but very, very close to 0. I'm using numbers between 0 and 1 divided by 2 to the power of 48. So numbers which are very, very close to 0. And now doing the LU decomposition and doing forward substitution and backward substitution, our result is horrible, as I will show you soon. I will show you. Okay, so here we are in my script. Here we have a matrix, 100 lines, 100 columns, consisting of entries which are uniformly distributed values between 0 and 1. And then we take a block, the first 10 lines in the first 10 columns, we take much smaller number, 2 to the power of minus 48, very close to 0, times some random numbers. So now we say if xl is the solution vector, then we calculate the right-hand side belonging to that solution vector, and then we call our LU simple algorithm, and this algorithm will not crash because we have no zeros, but the results which were produced were that. So the first entry for our x vector is minus, in my case it was minus 1111 instead of 1. The second entry was 941 instead of a 1. The third entry was 88 instead of a 1. This entry was not that bad, it was only 1.5 away from the correct value, but that means that all these entries are complete nonsense. And this is kind of miracle. When I saw that, I was not able to believe, and the only way to believe that was to call it in my MATLAB by my own. I think it's impossible to really believe what I show you. So you should run the code on your computer and then you will see. And there is no error anywhere. There is no error in the programming. The error which we see here must come from something else. And that something else are rounding errors. Is that possible that we see these horribly bad rounding errors? That is unbelievable. If we want to understand that, let's examine that example. This is our matrix from before, but instead of a 0 in the first line in the first column, we use a 0.001. And let's assume that the floating point numbers are of the kind that we have 3 significant digits, not 16, but only 3, so we can more easily understand the effect. What does that mean, having 3 significant digits? So that means that 5234 can't be stored exactly, but this number has to be stored to the rounded version, and the rounded version, 3 significant digits, is 5230. So let's recap a little bit theory about floating point numbers. This number can be stored exactly, that's no problem. We can store it as 4 times 10 to the power of minus 3. And this number can't be stored exactly. Here we will also have rounding, because after the first digit, the 5, we will have 2 more digits, but the third digit after the 5 is not possible to store because we assume floating point numbers with 3 decimal digits. That's a simplification, but it's very useful, this simplification, because now we can do all these calculations and see what happens. Okay, and let's simplify one more thing. We don't check the LU decomposition, but we check the simple Gauss elimination. Believe me, I did the same check for the LU decomposition, and the result in the end will be exactly the result we see here, but then it would be a lot more writing, and so let's check the Gauss elimination process. Okay, if we have that, we copy that line we have here, and now we want to kill the 1. How to kill the 1? We divide these two numbers, and so we get the factor 1000. And so we take the second line and subtract the first line multiplied by 1000. If we do that calculation without rounding, then we get here our 0, okay. And what do we get here? Here we get 1001, which has to be rounded, and it would be rounded to 1000. And here, the right-hand side, 1000 times minus 3, and then 5 minus that number, so we get 3005, and this number will be rounded to 3010. And then we have our LU decomposition, or our triangle structure. And then what do? We calculate x2 by dividing 3010 divided by 1000, and we get 3.01, which is very, very close to the exact solution. This solution is here, 3.001999 and so on. And our calculation gave us 3.01. So far, everything is great. But now we do back substitution, and we take the first line, we take the minus 3 from the right hand side here, and then we subtract minus 1 from here times our solution for x2, which is 3.01. And then what do we see? There is minus 3 plus 3.01. And what do? We subtract two numbers which are very, very close together, and that is numerically a bad idea, because subtraction working with floating point numbers is a very, very bad idea if the numbers are very close. So in this case we get 0.01 divided by 0.001, and in this case we get a 10. So our solution for x1 is 10. And what is the correct value? The correct value is more or less 2. So we get a 10 instead of a 2. And what do we see? The last entry is more or less okay, but the first entry is a catastrophe. And that is also what we have seen here. The last entry is not the big catastrophe, it's a catastrophe, okay? But the first entries are even worse. But that doesn't matter which ones are the better one and which ones are the worse one. What we see is that our solution is a catastrophe if we have numbers close to 0. And that was the case with our real MATLAB, where we have 16 significant digits. Also, we saw big problems, and the problem comes more or less from here. Do you remember? We did 1/3 minus 1 divided by 7, and the answer, the correct answer, is 0.190476, and so on. And now adding a large number to a third, adding a large number to 1 divided by 7, and then subtracting these numbers, mathematically the answer should be the same as we had before. But here we had rounding errors. We don't see the rounding errors here in that case in the numbers I wrote here, but the wrong digits are behind. But if you increase that number, then the problems were obvious. Then we saw we had big problems. And when I talked about that, I said nobody would be that insane that he will have the idea first add a large number to both of them and then subtract. Nobody would ever have that stupid idea. But here, in this case, using the simple algorithm, this will happen. This will really happen. Because why? Eliminating here that entry with the first line, then we need a very large multiple of the first line. And that means that here we add a very large number coming from here, that line times 1 million plus this entry, and so we add a very large number here and here and here and here and here and here and here also. And then also in all the other lines. And later we will use that entry to eliminate here, and that means that we more or less get rid of the large numbers, and so we have a situation which is very close to that situation. Okay, in our example we can really get rid of our problems by swapping the first two lines, as I will show you. Swapping the first two lines, we will be in that situation, and now if we use the first line to eliminate here, then we will do that. We add a multiple of the first line, and then we will have these results. Please redo these calculations by yourself to really understand what's going on. And then we get x2 is 3.01, which is very good, and x1 is 1.99, which is also very good. So we get a perfect result here with that idea. Let's swap the first two lines. And what was the concept? Don't use small entries here in position 1, but instead use large entries. And this is our principle we will follow. This is our idea, and then we can check if the problems are healed. So let's reprogram our code. Now we will call a modified LU decomposition, and now we need an index for the swapping of the lines, and then we will use the forward substitution, but we will have to swap the right hand side also, and then we will do the back substitution. And now the interesting code is our LU decomposition, and this is our index vector first. Okay, no swapping of any lines, and then we need the L matrix. Last time we used the identity matrix to start with, but we need to put the ones onto the diagonal in the end. Okay, now we run our for loop, and now we will find out which is the largest element in the first column in the first run of that for loop. Then we will swap the first line of A with the line holding the largest entry of the first column. But don't forget the abs. And we also have to apply that swapping to the L matrix. and we also have to keep track which changes we did so far. And now we do the elimination process after the swapping, and this is a copy of the code of last time. Then we add the ones onto the diagonal, and the rest is the same we had before. Now we can test our code, and let's check if that idea helped. So far it's an idea, but we don't really know that we can be sure that the problems are healed. So let's check. Let's have our coefficient matrix. Let's have our right hand side. Okay, let's use this time not ones of the XL because of all these swapping operations, and maybe it would be better to have different numbers here in XL. So let's call LU simple, and let's check the difference of our solution with the correct solution, and then let's call our modified version, and then let's check what's going on here. And for our first example, we have the horrible answer 3900. When I ran that code, this was the answer. If you do the same, you will get some different large number. But then our modified version, that gives us a very, very small error. So it's fantastic. It really helped, and our problem is solved, at least for that example. And this strategy is called column pivoting. Sometimes students confuse column pivoting because maybe this means swap the columns, and that is not true. We will see swap of columns in the next video when we talk about total pivoting. So don't confuse column pivoting and total pivoting. So what did we see? We saw that we have problems with our simple programming, and we saw that these problems were horrible. Then we had an idea to get rid of the problems. We were not sure that it really works, but we checked for an example, and then the problems were absent. And in the next video, we will talk about, okay, is it guaranteed that the problems are healed or not? And we will see something more surprising. But this video is very, very helpful. This video is the reason why numerics is an interesting thing, because of the rounding errors. Rounding errors can produce problems which we don't consider, because in mathematics we don't see rounding. The concept of rounding does not exist in mathematics. It exists being an engineer, but it also exists being a user of a computer. And so we saw we have to carefully ponder about our algorithms, and we have to carefully check if they fail or if they don't fail. It would be a catastrophe if we program code and assume that code to be perfect because it is perfect if there was no rounding. But in the real numeric world, in the real Excel world, in the real MATLAB world, in the real C world, and whatever world, there is rounding. And so we have to be careful, and we have to scrutinize our code for problems, numerical problems. And that's what we do in this lecture about numerics.